Hello everyone, let's solve a problem from GATE 2015 Aerospace Engineering paper, question number 33. So the question is, the Reynolds number is defined as U infinity L by nu, where L is the length scale of the flow and U infinity is its reference velocity and nu is the coefficient of kinematic viscosity. In the laminar boundary layer approximation, the comparison of dimensions of convective term u dou u by dou x and the viscous term nu dou square u by dou y square lead to the following relationship between the boundary layer thickness delta and Reynolds number. So we have been given four options by relating the Reynolds number and the boundary layer thickness. The first one is delta is directly proportional to root of Reynolds number. The second option is delta is directly proportional to 1 by root of Reynolds number. The third option is delta is directly proportional to Reynolds number. And the fourth option is delta is directly proportional to 1 by Reynolds number. Right? So let's use the boundary layer equation, in which we will just consider only the convective term u dou u by dou x, and we will relate the dimensions of the convective term with the viscous term, which is nu dou square u by dou y square. Okay, so let us consider the flat plate boundary layer, which is simplest case for solving this problem. Let us consider L is the length of the plate, and we have a boundary layer forming on the from the leading edge of the plate. Okay, this is the boundary layer forming, and we will have a velocity profile like this. So we have u infinity coming in this direction, which is the free stream velocity. Okay, so this is the thickness of the boundary layer, and we have the velocity profile forming like this. Okay, it goes from 0 at the wall and till u infinity at the edge of the boundary layer, right? So this is what we will have. So we'll use all these parameters to define our dimensions for each of the term in this convective and viscous term, and we will just relate u with u infinity, and we will relate x with L, and we will relate y with, we have del bar, which is del bar is equal to del by L. Okay, we are just going to use this in this equation to find out the relationship between the delta and Reynolds number, and we know that the Reynolds number is u infinity L by nu, which is also given in the question. Okay, now let's substitute instead of u infinity and u infinity by L, and which is proportional to nu, u infinity by, we have y square, so we have L square. Okay, so this L square will come this side, and this u infinity will get cancelled. L square by L, so these two will get cancelled, so we'll get L here, nu by del square. If we just want del square, then we will get nu by u infinity L, right? So this is proportional to 1 by Reynolds number. As you can just see, the formula for Reynolds number is u infinity L by nu. So we have inverse of that, then we will have 1 by Reynolds number. So we just want delta, which will be proportional to 1 by root of Reynolds number. Okay, so this is the answer. Our boundary layer thickness inversely proportional to the root of Reynolds number, right? So let's go and see the options. As you can see, from option B is having the correct answer, so that is the correct option for this question, right? So if you want to know more about the boundary layers, you can refer to the NPTEL course Introduction to Boundary Layers by Professor Rinku Mukherjee at IIT Madras, and you can also refer to the video of from week 3 and module 13, which is relevant to this particular question. The title of the video is the derivation of Prandtl's laminar boundary layer equations, and you can also see the YouTube link for the particular lecture here. Okay, that's all for this question.